Hello everybody. I would like to welcome you to our virtual lab tour. My name is Sebastian, and within the next 15 minutes I'm going to give you an insight into our research activity at the project group Cognitive Material Diagnostics at the Brandenburg Technical University Cottbus-Senftenberg at its site here in Cottbus. The laboratory belongs to the chair of Communication Technology from Professor Matthias Wolf, whom we have close collaboration with. Come on in and I show you our demonstrations. The first demonstration will be given by my colleague Dario, and the demonstrator will adequately show the possibilities of machine learning.
Thank you, Sebastian. The demonstrator consists of a tray and the microphones arranged around it. The microphones are connected with a Surface Go, which does the classification work. When the coin is dropped, the impact noise on the rippled glass surface are recognized by neural networks for each microphone channel separately and are then combined for the best recognition rate. Let's throw an €2 coin. It is recognized as a €2. Let's take another example, a 2-cent coin. Also correctly recognized. Last but not least, we take this coin. It is correctly recognized as 2 cents. If you throw another coin, like a 4-An coin, inside it, it will correctly be rejected. This is a little bit of a trade-off between recognition and a rejection rate. For training, we have had 8 coin sets from different Euro countries, from 1 cent to €2, and each coin was dropped 200 times. Back to Sebastian.
Thank you, Dario. Our next demonstration is our ultrasonic testing rig. This testing rig was co-designed and built up by one of our students. In our research group, we focus on the combination of non-destructing testive methods and the associated data evaluation using machine learning. A current research focus involves the testing of sinter manufactured gears for internal flaws and imperfections using this test rig. The idea is to have a machine learning model which later can characterize the internal flaws, and the research focus is that we would like to, or we're working on filling the vast amount of measurement data, or even replacing this measurement data by computer-generated data, so-called synthetic data. For that, we perform simulations of this test setup, which you can see here, a visualization of one of the ultrasonic simulations of the sintered gears. The idea is to have at the end a fully trained model just by synthetic data or combination of synthetic and measurement data to classify these internal flaws. Another test that has been performed on this setup was the acoustic resonance testing of sintered cogwheels, as you can see here. This we've just seen, this is the cogwheel setup. We perform the measurement. Then we do a primary and secondary feature analysis, seen here, and then our models are trained. We use one-class classification and binary classification, and here you can see a test result of a support vector machine, and you can see that our model is able to classify intact and imperfect cogwheels, and the further we have the spread of these two groups, the better our model is. In our next presentation, my colleague Ilkin will present to you a fairly new research field, the digital twin.
Thank you, Sebastian. Digital twin is a fairly new trend in industry. It allows to replicate, to mirror the real physical production devices on our computer. For this purpose, we need very, very fast computer models. They should be as precise as the physical models that Sebastian just showed, and he showed a simulation of ultrasound wave propagation. But on the other hand, they have to be lightning fast. To achieve this, we use a method called reduced order modeling. I will show a very simple example on ultrasound signal propagation of a plate. I'd like to show first this experimental setup. We have one sender and one receiver, and the third needle is passive. It doesn't do anything other than support the plate. So now we lay the plate on it. So how we build a digital twin of this simple plate? First of all, we calculate all of the relevant MODIs using a model analysis. In this example, we went up to 350 kilohertz. So our digital twin will be capable of imitating ultrasound wave propagation up to this frequency. After we calculate these MODIs, we overlay all of those MODIs on top of each other, and we have a reduced order model of this phenomena. It is as precise as the full-scale simulation, with one exception, that it is reduced only to 3 points. We can only read the results from the 3 points. We have one sender, one receiver, and the passive needle that we saw on the real thing, in this case, is also an active receiver. So in this way, we even created a virtual sensor. In reality, we weren't able to read any data from this receiver, but in this model, we are able to. Let's look at this. In our model, we are able to send any kind of ultrasound signal through our receiver, and our model shows the response from those two receivers. One of the lines show the receiver 1, and another line shows the receiver 2 timed response to the signal. To the right-hand side, we can see the frequency domain response, which means we are able to see the response to any kind of frequencies coming from the sender. Thank you very much. That's all from my side. Back to Sebastian.
Thank you, Ilkin. My next colleague, Max, also works in the field of ultrasonic testing, however, in a more industrial context, and he will give you the insights of our project CompWatch.
Thank you, Sebastian. In the CompWatch project, we investigated compressors for automated monitoring. This is done to allow predictive maintenance work. So we predict the condition of the compressor and its future development, and therefore then plan ahead or plan necessary maintenance. And this is in contrast to the preventive maintenance that's usually used, where there are strictly planned maintenance intervals and some additional work that needs to be done if there are any faulty behavior in between. With our developed methods, we can extract some score that allows us to indicate how well one compressor performs right now and how much it differs from normal behavior. The higher the scoring, the better the condition, and the lower it gets, the worse the condition will be. This can then be used to either detect faulty behavior that we either simulated during our monthly our recordings over a few months, or are occurring due to the working environment, like to a lot of dust in the area also. The other trend you can analyze is the downwards trend of this graph that allows us then to experience the effect of wear and then also plan ahead when to do any special maintenance work. All in all, this developed method of us can be used to assist and therefore guide maintenance work, and should be further improved in our future work and also expanded on other machines other than compressors. Okay, thank you, and back to Sebastian.
Thank you, Max. My colleague Matthias will now present to you our research activities around predictive maintenance.
Thank you very much, Sebastian. As part of our BMBF-founded research project DispoV, we are developing a condition monitoring and predictive maintenance system for rotating machines and industrial mills. And the hardware side of this prototype is presented here on this picture. And this prototype is currently, or will be currently installed at the power plant Boxberg. Here you can see the coal mills and their positioning, different pumps, as well as the sensor network as the system for the data processing. As an essential component of our project, we are interested in the wear analysis, and therefore we use this operating and event data. This data contains the operational use of the machines, and then we combine this data with various sensor data to a wear model, which is presented here. The complex operating and wear conditions, to classify these complex states, we are using deep learning, and based on this deep learning we are developing and testing and optimizing different procedures for predictive maintenance. And our aim is to get at the end a system which replaces the manual and time-consuming inspections by an automated and continuous condition and monitoring system. Thank you.
Thank you, Matthias. This was our little lab tour. We hope you enjoyed it. If you have any questions, feel free to ask them. Thank you very much.